Hello. This is Crockett Hensley's submission for the second programming assignment, if you want to call it that, for the Dr. Hung's AI course. So the assignment, I'm assuming that Dr. Hung is probably the only one watching this, but if anybody else ever watched it, the assignment is to make an 8 puzzle solver using a bunch of different methodologies, different search algorithms, which let me actually pull up the assignment. So that's the assignment. Just finding with depth first search, uniform toss, breadth first search, A-star algorithm, what all these different, essentially the node complexity and the average runtime. I'm kind of just doing this by Monte Carlo method, where I just run it a bunch of times and see. So because of that, I do have this interesting limitation where I can only do a few runs until it the complexity is so great that it takes a really long time, and I don't necessarily want to do that. So right now I have it set to where it'll just do you'll just have 10 of each. I could potentially increase that, but that gives a lot of flotation in the final numbers, which you'll probably see in a minute. Anyways, essentially the way that I've implemented this is I started by creating a game board class, an 8 puzzle class. This was actually something that I made a while ago for a friend, but I updated it now for my own use. And essentially the way it works is whenever you create a board, it has a way to create a board from another board. So if you do that, then it keeps track of your ancestors, so it can just like recursively go back and find what board generated what. And that essentially allows you to just use a move function within the board object to generate whatever the next board object would be. It is a hashable object. It's we've got equivalence, representation, all that good stuff. But essentially, all it does is it creates a randomized board, a randomized 8 puzzle board, which is just like a 3x3 grid full of 8 essentially slide tokens. 8 tokens that are like a slide puzzle. And there's a lot of different versions of this game. Usually it's the version that we're using in this class, the empty tile is supposed to go in the middle, but I made this kind of generic. The target one puts it in the middle, but I designed this generically to where you can set the target board to be anything, and it should still work just fine. So what this does is it randomly generates a board. That board is not guaranteed to be solvable for any particular configuration, which I ran into a lot of issues with that, and I eventually came up with another solution, which I'll show you how that worked in a minute. But it essentially generates a randomized board using random.sample on the list of board tiles that you can use. And then it has this thing called enumerate moves, which essentially just looks at if you're, depending on if the blank tile is in the corner or side, which moves up, down, left, and right are legal for you to do with that particular board. And then it just gives you a list of all the legal moves. And then we have move, which can take either a list of moves or a just one specific move. And what it does is it generates, or it doesn't have to be a list, it can be any iterable. But what it does is it generates a new board for each different direction command that you pass to it. So the way that this is supposed to work is you just say current board.move in the direction current board.enumerate moves, so that will just explore every different possible board and generate an iterable object that has basically every possible move you can get to from a certain board. And when it creates them, it will make the ancestor self. So it will just create this recursively linked tree that you can climb back up with get ancestors to figure out where each board came from, which I used for kind of debugging. And if you want to, just let me know and I can show you how that all works. But it doesn't actually come into play for the program because it wasn't requested in the actual assignment. So then we just have some more kind of quality of life things. This just easily gets the number of, it's basically the number of generations that the board has been through, and this just gives the like positions of the board in list form. And the way that the list form is supposed to work is you have all these guys. This is essentially the first three are row 1, the second three are row 2, the third three are row 3. So that's why this would have the blank tile in the middle. It's also why these numbers are actually out of order for this particular target board. They're not just 1, 2, 3, 4, 5, 6, 7, 8, 9. They're actually 1, 2, 3, 8, none, whatever, because that's just row by row. So now let's talk about the solvability of these. So when you have an 8 puzzle, it is mathematically impossible to solve it if the target board is an odd number of swaps, of tile swaps from the original board. So essentially what this does is if you just randomly generate a board, there's a 50-50 chance that the algorithm will just churn and churn and churn forever and never stop. So I tried to come up with a method that mathematically predicted what to do, and it would just mathematically figure out whether the board was solvable or not. But that didn't really work. I'm not exactly sure why. It may have actually worked. It just, some of the boards were really, really hard, and they took a really long time still. But what turned out to be much more reliable from just a actually getting the program to run and finish in a timely manner standpoint is to do this generate solvable. So I can pass in what I want the target solution to get to, and this will generate a board that's guaranteed to have a relatively simple solution by essentially just taking that target board and making random moves on it a certain number of times. So that's what this max moves is. This is essentially how much it scrambles it up. And I found 30 is about a sweet spot for where most of the algorithms have to work a little bit, but you can increase it more and they will, as the board gets more scrambled up, the algorithms will take longer. That being said, I don't want this video to go for 10, 20 minutes while I wait. So we're just gonna leave that at 30 moves for now. It still might take a minute or two for some of these, because I am running them 10 times each. But what we have here for the depth first search, I generate a target board, and then I make the starting board using this generate solvable function, set up the times. Oh, frick. Huh. So that's why that was being weird. So these were always, this one was always taking way, way longer. And that's because that is supposed to go in there. Yeah, sorry, this code is still kind of a work in progress. All the rest of them have that, right? Yeah, okay, so that was just the clocking time. The depth first search was consistently being a lot longer amount of time, and that would explain why. If you didn't notice, what I had done is I had set the timer function and like the node counter to be, it wouldn't loop when the program started over to check again what the time would be for the averaging. So Yeah, that's fixed now. Can't believe I caught a bug on camera. That's a rare event. Um, so yeah, essentially it gets a double-ended queue here to keep track of what boards need to be checked, and then it checks if the board that it currently is looking at is the target, and if it's not, then it finds all the boards that it can get to from there, and assuming that it hasn't hit this depth limit of 100, which shouldn't happen, it will, and also assuming that the board hasn't been already examined at a higher up level in the search tree, which is what this is. This is checked boards is just a dictionary that keeps track of every board that's been searched and at what level it's been searched. So, assuming that there isn't, that it either hasn't been searched yet, or it was searched at a lower down level of the tree where it might hit a depth limit or something, it will check it will add those boards to a list of boards to check, or to that double-ended queue, I should say. So then it just pops boards off the same end of the queue. So this is a first in, last out search, or first in, last out data structure, I should say. And all it does is it saves it in the checkboard so that it can get the dynamic programming element, which really helps accelerate this. And then it goes until it eventually finds one. So breadth first search is essentially the exact same code, except instead of appending directly to the double-ended queue, it just appends it to the opposite end of the queue, so it's now a last in, would that be first in, first out function. That'd be a first in, first out data structure. So you have the first few, like whatever the first row of searchable sort of branches of the search tree, those ones are going to be checked before it moves on to the ones further down the search tree. So this usually takes a little bit longer, but it's guaranteed to find the shortest possible solution. And there is also a similar dynamic programming element to it here, which is just that if it's been searched before, it won't be searched again because it searches from the root of the tree down. So if it's already been looked at, that means it was already looked at some point that's higher up in the tree. So there's no point to check it again lower down in the tree if we've already been there. UCS, uniform cost search. In this case, there's no actual costs associated with the breadth first search. So there's no actual costs associated with checking each node. The costs actually are uniform. So this is the same code as breadth first search. I'm actually not exactly sure why we were even asked to do a uniform cost search. Because uniform cost definitionally is the same as breadth first search in this particular case. So I put it in anyways, but just know that it's the exact same code as the breadth first search. Yeah. So what we have after that is we have the A-star algorithm, and we weren't provided with a heuristic for the A-star algorithm. So I went ahead and programmed Nilsson's sequence for the heuristic, which was something from the slides. And it's a very good heuristic for this kind of thing. So what that does is Nilsson's sequence, basically given a board and the board that you're trying to get to, will start by computing the Manhattan distance. And that's what all this is. I haven't really commented up all this code yet because I'm gonna have to submit this pretty soon, and I just wanted to get the video out of the way. I'll throw in some comments for the PDF if I can. But essentially all this does is it goes through each tile in the board that you're trying to compute the Manhattan distance for, and uses modular and integer arithmetic to figure out the number of rows that it is different and the number of columns that it is different. It adds those up for all of them, and that's the Manhattan distance. And then it does the sequence. So the Nilsson sequence is, this is just basically the clockwise adjacency of that one-dimensional matrix. And it goes through each element in the board except for the center element, which is why we have these two different slices of the list. That's just cutting out the center element. And then if the tile that's next to it is in the center, or is essentially if the next clockwise element in this board is not the same as the next clockwise element in that it has in the target board, then we add 2 to the sequence. Otherwise, and then at the end, we just take the center one and add 1 if it's not what it should be. So then we just return this linear sum, or linear weighted sum of the sequence and the Manhattan value, and that is Nilsson sequence, just very simply coded up. And that's our heuristic for A star for the informed search. For A star, we have just the same kind of thing. We have the target board, tracking stuff. We're getting the runtime, number of nodes searched, all that. We have the current board is make sure that it's a solvable board. The non-solvable boards cause me so much trouble. And then we just go through, and for each board that we can get to from the current board, we just evaluate its value using that Nilsson heuristic. And then we add essentially the number of levels deep in the search tree that it is. So that's the A star, because the heuristic value plus the G value. So this is the G value here, and then the heuristic is this Nilsson. And then if that's basically assuming that we haven't already found that board before, or that particular board sequence before with a lower heuristic, we will add that one to the list. Or to the dictionary, I should say, because hash mapping is very important for this. I tried to do it with lists, and it didn't actually improve the runtime much at all. In fact, it might have made it worse. So yeah, hash maps. Hash maps are good. More tracking stuff. This is just, we find the most promising node using simple minimization. Then current board is just set to basically one of the appropriate key of the basically any one of the appropriate keys. There's not technically any guarantees in this, I think, but because it's a non-sequential data structure, so there's no guarantees as to which key will be chosen, but it's just one of the keys that it has a value, a total heuristic and G value that is the minimum will be chosen for being the next board to be expanded, and then that is removed from the list of boards that we need to check, but it stays in the list of boards that have been checked, so we can still dynamically program. So yeah, I added this little thing where at the end of each one it'll just print out to the console, which like essentially when it completed. So A star usually completes first. But yeah, I have a lot of cores on this PC, so I decided to set up all this parallelized because it was going to take forever otherwise. Yeah, so that was a pretty quick run. So it's just 10 of each. This is the number of nodes that it generated. So depth first search generated like 8,000, breadth first was like 1,500, UCS was like 1,400. A star only opened 24 nodes. So A star was actually able to find a solution that was a shorter number of moves than the number of random scrambling moves that we did, which is pretty common. And that took a very, very short amount of time, as you can see. Slowest was the breadth first search, which is kind of surprising to me because we actually opened more nodes on the depth first search. But yeah, there's a lot of play in this because breadth first search and uniform cost search are technically the same in this particular example. I can actually change it. Let me change it to run some more copies of these. Let's just change it to 20 so we can get a little better idea. Slightly more stability in that Monte Carlo that is our generation. And realistically, I probably could parallelize even more, but do I really want to? Yes, but I don't have time. So, see, A star still completed pretty much instantly. DFS still completed pretty much instantly. I can see like this is using not that much processing power, all things considered, although I do have 12 threads on this machine, so considering this can only use 4 of them, that's about all we would expect it to use. And so you can actually see here when each thread completes, we see a drop in CPU activity. So there's just a spike at the start when it's running A star, and then it kind of drops off over time. So yeah, eventually that will finish. UCS, for some reason, UCS is usually UCS and BFS usually take the longest. I'm not sure if that's because of the way that the dynamic programming worked out, or if it's because of just the nature of those things. That even though DFS usually opens more nodes, these two take longer. But it'll finish eventually. I hope to God. So yeah, this is all just formatting stuff. And we have, if you're not familiar with what Python multiprocessing looks like, this is a kind of scuffed representation of how to do it, if I'm being honest with you. I'm using pipes to get return values because getting return values is for some reason really overcomplicated in Python's multiprocessing. And I can't just use normal multi-threading because normal multi-threading is still using the Python executable, which is single-threaded for some dumb reason. But yeah, that's basically it. I suppose I can show you a little bit more of this while the UCS is still trying to finish. So we have, essentially this is just doing some linear, this is doing some simple arithmetic. Oh, I finished. Yeah, so this is just doing some simple arithmetic to figure out whether a board move would be legal for uses left, right, up, down as the moves. So yeah. Anyways, as you can see, UCS was the one we were waiting to finish, and that generated over 3,000 nodes. Interestingly, DFS averaged two nodes. So it must have gotten very, very lucky on the scramblings. This doesn't scramble the same boards for every one of them. Each one has their own randomly scrambled set of boards. So, oh, freak, that's why. Heh. So it's solving the same board over and over again. Yeah, my DFS implementation was the first one to come out. It's not great. But yeah, that one just got really lucky on the first one, and then it finished like immediately. But A star averaged 17, which is pretty good. But yeah, this guy took like 8 seconds per to get through, which is pretty bad, all things considered. I do kind of wonder about that. But yeah, maybe it got unlucky on the generation. There's no telling. If breadth first search has to get up to about 30 or so moves, then it really starts to slow down. It can take 10-20 minutes to actually hit 30 moves. Usually I'm counting on the fact that the breadth first search will hit the appropriate, it'll hit the appropriate depth to reach solution in 18 to 22 moves most of the time if I have the maximum move set to 30. But again, if it gets lucky and it doesn't back up on itself very much, it's just kind of random walking over the 8 puzzle moves. So if it doesn't back up on itself very much and it ends up a lot of moves from a solved state, then the breadth first search can take quite a substantial amount of time because the max moves of 30, if it has to search 30 degrees of separation, that's quite a lot. Usually it kind of slows down at 20. So yeah, that's my program. Let me actually run it again just so you can see the depth first search behaving in a way that is a little more normal and not just solving the same one over and over and over again. But in principle, it all works. I will try and get all this commented up as quickly as possible. I've got about 45 minutes before I'm supposed to submit this. So this YouTube upload might go up slightly late. The YouTube upload speeds are not always awesome. So I'm just kind of trying to kill a little bit of time while this completes. Breadth first search done. Yeah, depth first search really is the most random one now that I've actually moved it to solve a different board every time. There we go. Okay, so yeah, depth first search had to search an average of 105,000 nodes. So that makes a lot more sense. So that's why all these numbers were like 8,000. Yeah, where it has one time it averages 8,000 nodes, one time it averages 2 nodes. That's because it's solving the same board over and over again. But yeah, average of 105,000, processor time 3 seconds. So this is pretty normal. Again, there's still a lot of swing in these two, but A star is always lightning fast. So hats off to Mr. Nilsson for coming up with this beautiful piece of code. He made all of our lives easier and faster. And yeah, hopefully this is sufficient for whatever your submission guidelines are. I know that the assignment isn't always super clear on exactly what you're looking for, but I really hope that this has made it very clear, and I will try to comment up and add doc strings to everything so that you can really tell what's going on here when I submit the PDF later. So yeah, that should be all. Have a great day, or honestly night, because it's like almost 11 o'clock.